linear drag. So we're doing linear drag, and I've already done 2 videos, and I'm going to build on those 2 videos. So the first video was I looked at the motion of an object with linear drag and no gravity, and then I looked at it with gravity. So what do we mean by linear drag? Well, let's just talk about, let me go ahead and jump into our 2-dimensional case, and then I'll go back to the results that I've already put on the board, and the videos will be linked down below. Okay, so suppose I have a ball, and I have limited space, right? Because I'm using all that for all that complicated stuff. So I have some ball, and I have it thrown with some initial velocity v0, but so over here, and then at some point it's in the air like that, and it has 2 forces acting on it. It has the downward gravitational force, mg, and then there is a backwards pushing drag force. I'll call that Fd, and they're both vectors. Okay, so we know the gravitational force, we're fine with that. We're going to say Fd, the drag force, is negative b times v, where b is a constant and v is the velocity of the object. And in fact, we're going to actually go a little bit further. We're going to say b is equal to beta times d, the diameter. So that's for a spherical object. This works, and that way I can look up some actual values, and we can use some actual numbers for some actual things. Beta is a constant depending on the fluid and the shape of the object, and d is the diameter of the object. Okay, so how do we model the motion of this object in the air? Well, you know I'm going to do it 2 ways. You know I'm going to do it the analytical way, and then I'm going to do it the Python way. And bonus, I'm going to actually make a 3D model of it also. So we're going to do all those things. It's going to be so much super fun. Okay, so let's go ahead and write down Newton's second law for this object. Let me move that ball over here so I have more room, because I'm space limited. I've already said that. So here's my mg, and then that's my drag force. And Newton's second law says that F net would be Fd plus mg equals ma. Okay, so those are vectors, right? This is the sum of the vectors. Don't put gravity as negative for 2 reasons. One, we actually called, in our results over here, we called positive y down, but that doesn't matter. These are additional vectors. They may have a negative or positive y component, but that's not the point. Okay, so we add them up and equals a constant. Now, let's look right over here. If we call this the x direction and that the positive y direction, then I can break this into components, into x and y components. So let's write Newton's second law twice. I'm going to write it for the x direction. This says F net x is going to be, well, what forces are acting in the x direction? It's just a component of the drag force. So I'm going to say this is equal to Fd x, the x component of the drag force, and that's mass times acceleration in the x direction. Now I'm going to do the same thing. F net y, and I'm calling down as positive, is going to be equal to mg, right? The gravitational force is in the y direction. And then I have a y component of the drag force. So in this case, that would be plus f dy. And the f dy could be positive or negative, and that's mass times acceleration in the y direction. Newton's second law, right? Now, notice that since the drag force Fd is negative bv, well, if v has x and y components, Fd has x and y components, such that Fdx is going to be negative b vx. Fdy is negative b vy. So we can separate the force into an x and a y component based on the x and y components of the velocity. That's super useful, because now up here I can write this as negative b vx. That's important. And over here I can just replace this as negative b vy. That's important. That's important because we solved that equation. We solved the equation for when you had a linear drag force and no gravity. We did that, and you can watch the video again. I'm not going to redo it. we found that the velocity as a function of time was v0 e to the negative bt over m, and we got a function for the position as a function of time. It wasn't impossible, okay? It wasn't that bad. And then we did this problem too. We already did that problem. With gravity and positive y is down, we got the velocity as a function of time, where vt is the terminal velocity, and y is the position as a function of time. So we did it. So the great thing is, just like normal projectile motion in physics with no air resistance, we can break the motion into an x case and a y case. So now let's just imagine that I want to find out how far an object goes. So how would I do that? So here's my object. I'm going to say it starts with some initial velocity v0. This is the positive y direction, and that's the positive x direction. So it's going to go up here like that. So I can break this into an x motion and a y motion. And if we just talk about positions, I'm not going to write out the full function. But the x motion, I have x of t equals all that stuff. It's not that bad. Okay, but I have that. So if I know t, I can find out how far it went. And for the y motion, suppose I'm on level ground, y is the function. Let's put the y motion over here. Y is a function of time equals all that stuff. All that stuff. So it's not trivial, okay, but I could do it. What I could do if I want to find out how far it goes, I could take this function, I could put in my final y is 0, my initial y is 0, and then I can use that to solve for the time. Not easy, okay, because 0, 0, there's a term right there, a term with t, and then an exponential, okay. So I'm not actually going to plug that in because I want to focus on the model more. I want to show that these equations do indeed work. So I'm done. I don't have to do anything extra. I already did all the hard work, right? What I want to focus on is modeling this. And so I want to model the motion. I want to also model the analytical solutions and compare them with the 3D model. So it'd be kind of fun. Okay. Now, for a numerical model, just like before, we're going to break it into short time intervals. During those time intervals, we'll assume the acceleration's constant so that we can calculate stuff. But we do need some values, right? We need some numerical values. So let's do the following. I'm going to use a tiny drop, a tiny ice ball, right? So I know the density of ice is 1,000 kilograms per cubic meter. I know and I'm going to use that. I'm going to use a diameter of 0.2 millimeters. And then finally, I'm going to use, and my beta. I have a beta. Beta is, I looked this up, 1.6 times 10 to the negative fourth. So that's my diameter. With beta, I can find B. And then with that diameter and that density, I can find the mass. Now, what velocity am I going to launch it? I haven't really decided on that yet. Let's say I throw it with an initial velocity v0 of 5. I just picked that. 5 meters per second at a 45-degree angle. Okay, so I'm first going to build the numerical model just using a small time interval, because that's going to be the easiest. But I'm going to build it with a 3D representation also. And then we'll come back in and check it with these equations right here. So let's get to it. Okay, switching to Python now. See, I'm in Python. Okay, so Web v Python. Let's just start entering our constants. I'm trying to decide here how I should do this. Okay, let's just say beta equals, what did I say? It's up there. 1.6 times 10 to the negative fourth. 1.6 times 10 to the negative fourth. D is 0.2 times 10 to the negative 3. Rho I is going to be, I can just say rho because there's the other beta, the density of air is taken into account in the beta term. So that's 1,000. Okay, now I need the volume. V is going to be equal to 4/3 times pi times r cubed, which is going to be d over 2 cubed. And then the mass is going to be rho times v. Okay, I know that's a long way to do it, but who cares, right? I don't have to do it all in one step. Now I need the gravitational constant. I'm going to write this as a vector. G equals vector. Now, I am going to use the normal convention as up as positive, just because I can't handle it if I switch that. 0, negative 9.8, 0, and then the other one we'll figure that out. Now I need, let's go ahead and make my ball. I'm going to just call it a ball. So the ball is a sphere, which is a 3D object in WebVPython. Its position is going to be at the origin, vector 0, 0, 0. Its radius is going to, got to put a comma there. Radius is d over 2, and then I'm going to give it a color. I'm going to give it a color of color equals color dot cyan. I mean, it's ice, but and then I'm going to do make trail, and you can't see that because my fat head's in the way, equals true. There. Okay. So let's just run it, right? Let's run it now. There is my ice ball. And of course, WebVPython zooms so that it takes up as much space as it can. So even though it's tiny, it looks not tiny, and that's fine. Okay. I didn't even save this. Air projectile, and it's all messed up, but that's fine. I'll fix it later. Oh, I almost got it right. Okay. Now I need I already have the mass. I'm just leave the mass as its own term. I need the initial velocity. I'm going to do it with velocity. So let's say V0 is 5. Theta is 45 times pi divided by 180. I want that in radians, not degrees. And so ball dot v, the velocity of the ball, is going to be equal to V0 times vector cosine theta sine theta 0. So now I have that. I think, oh, let's calculate b down here. B is equal to beta times d. That'll make things a little bit easier. Okay. I think I'm ready. Oh, nope. T equals 0, dt equals 0.001. I'm going to do a little bit smaller because I'm dealing with small things. I don't think it matters too much, but let's just do that. While t less than 1, I don't know how long it's going to take. Rate 1000, so rate tells me how many calculations to do per second so that it will run in real time. We can change that later if we want to, but that's fine. The first thing I'm going to do is to calculate the net force. F net is going to be equal to m times g, right? That's the weight, minus b times ball.v. That's it, right? And so I want to point out that ball.v is a vector, g is a vector, has a negative y component, so F net is a vector. So it's all good. Now I can use that to update the velocity of the ball. Ball.v equals ball.v plus F net times dt divided by m. I need the acceleration force divided by m. Now I can update the position of the ball. Ball.pos equals ball.pos plus ball.v times dt. Finally update the time. T equals t plus dt. And let's run this thing and see what happens. Oh. I think it's okay. I think it went up. It went up and then it just fell straight down. And that seems kind of reasonable. I think the zoom out thing kind of messes up a little bit. I think that's pretty good. I'm pretty happy with that. You'll notice that it's hard to throw these things really fast, right? Because the faster you throw it, the more drag force you have and the greater it slows down. So you really can't get too much out there. Let's just change this time interval to 0.5 seconds. I think it's fine. Yeah, that looks good. Nice. And so we can actually plot the total position, but I'm actually going to go ahead and use the theoretical position function that we calculated before for the x and y direction to plot the trajectory. So I'm going to plot the trajectory of this as a graph, and then I'm going to do it analytically. And once we do that, that's a win. We've already done. Okay, we're winning. So up here, let's make a graph. G1 equals graph, x title, and this is a trajectory. So let's just go ahead and put this. Title equals ice ball trajectory, right? X tidal is going to be equal to x in meters, comma, and then I'm going to wrap it. Y tidal equals y in meters, comma, and then width, spell it correctly, width equals 400, height equals 200, and then I need to graph to plot. I'm going to call this F, this is called F1 equals G curve. Color equals color dot blue. Now down here I want to plot the trajectory in each time interval, F1 dot plot. I want to plot the x coordinate and the y coordinate. So that's going to be the position function of the ball object. So it's going to be ball.pos.x, ball.pos.y. No y. There you go. Let's see if this runs. Okay. That's good. Nice. Now for the hard part, because now I need to type in my initial properties. So let's go up here and give it an x0 equals 0, y0 equals 0, gg is going to be 9.8. Because I need to use g as a scalar value, and I don't want to have to take the magnitude of that vector, so let's call it a new variable gg. And then finally, I need vx0 is going to be v0 times cosine theta, just like the other one. And then vy0 is going to be equal to negative v0 times sine theta, right? Because I called down positive, and I think this will work, right? And then that's going to say it's moving in the negative y. I think then when I plot it, I'll need to plot negative y. I think. Okay. I could just write these as functions, but I'm not going to. Let's just do this the long way. I need another graph. So I need something to plot. F2 equals G curve, color equals color dot red. And then down here, I'm going to calculate xt is my theoretical x position. So I'm looking right up here at my graph, my function that you can't see, but you can look at the other video. It's going to be x0 plus vx0 times m over b times 1 minus e to the negative b times t over m. Right. Okay. And then yt is going to be, now this one's a bit longer, y0, which was 0, I don't need to do that, plus m over b. I'm going to make a mistake here. I'm letting you know right now. Times v0. Oh, I didn't calculate vt. So vt is going to be equal to m times gg divided by b. And that was something we did before. Like, so bvt, the terminal velocity, is when it's equal to the weight. Okay, so down here. V0, so it's vy0 minus vt, capital T, case matters, plus v capital T times t plus v capital T minus v0, vy0, times m over b times e to the negative b over exponent negative b times t over m. If this works, I'm just going to be like, what? Can't believe it happened. Okay, so now I'm going to plot that. F2 dot plot xt negative yt. I don't know if it's going to work. I did save it. I did save it. Let's save it again, though. Okay, here we go. Ooh, see? Didn't work. Undefined object. Okay, I just missed an asterisk, I think. I can handle that. Undefined object. Okay, go away. VT. Where was the undefined object? Let's run it. What did it say? Undefined is not an object. Evaluating V0 parentheses. Oh, I wonder if I, on V0. Oh, I took VO. I bet I did VO. If I did, that's just a crazy mistake. I'm looking. I have V0. Let's just do Alt F, VO. No, V0. Next. V0, V0 equals O. Oh, I see what I did. Okay. Control C. I used V0 before I said what V0 was. Dummy. Okay, that's fine. Aha. Okay, where's my red curve? It didn't work. Let's see. Let's turn off the blue and see if that works. I mean, it could be right on top of it. I don't think it is, but it's not plotting. Okay. Oh, boy. Made a mistake somewhere. Let's plot xt versus xt. Right? It should be aligned. So it'll at least tell us if xt is calculated or not. We can troubleshoot and find out where the problem is. See, that did not plot. Let's just try yt versus yt. See if that one works. That one didn't work either. Whoa. Let's do this. Print xt. Print yt. I'm sorry for making a mistake here, but you know, I think it's fine, right? Because we all make mistakes and we need to learn how to figure out what those mistakes are, or we could just give up and go home, which sometimes I want to do, and it's not a number. So that means I'm doing something that is illegal. I know what it is. I know what it is. I know what it is. No? Yes, I do. No, VT is MGG. Why is it not a number? Neither of these are. Negative BT over M. So I assume this is a problem right there. X0, VX0, M over B. 1 minus B. Is B positive? What do I put for B? B is beta times D. That's fine. Let's print B. Print B equals B. Print M equals M. I don't know. So those are fine. Okay, let's do this. The weird thing is that both of them, neither of them are printing. They're both not a number. X0, VX0, VX0. Oh, is that the problem? No, because it should be VY0. M over B times 1 minus exponent negative BT over M. Let's just copy this. Print. And I'm going to get rid of that. Let's just get rid of some of this. Let's just print this. See what happens there. Someone probably sees the error right now and they're like, you're crazy. Okay, so that worked, right? That's giving me a number. If I add in, that's fine. This does not like it. Why? M over B. Not a number. Oh, beta? Beta's fine. B. Now I'm really starting to feel dumb. Let's get rid of this part right here. This stuff. That says that if I included that, it wasn't a number. Not a number. Huh. So, something dumb here. Vx0. Vx0 is not a number. Vx0 is not a number. That's my problem. Why is Vx0 not a number? It's oh, wait. I did move that up there. It's V0 times cosine theta, print Vx0. I didn't print it. It's not a number. What is wrong with you? Oh, do I not have theta? Oh my gosh. That's why. The dumbest mistakes. See, it's just stupid mistakes. It's fine. It's fine. Everything's fixed now. Everyone could go back. We're fine here. Thank you. How are you? I know everything's fine, so I'm gonna try one fell swoop it. Stupidest mistake. There we go. What a trip. Okay. You know, another person would say, hey, I'm going to redo the video, but I'm not going to redo the video because this is real life. And that's that. I will give you the code, though, down below. There you go. It works. Pretty happy. Now, we do have one more thing that we could do in another video, and I probably will do this, don't know for sure, but that's like, what's the maximum range? How would you find the maximum range? It's not trivial to do it as a max-min problem. Not impossible, but it's easy to do it numerically. So I'll do it numerically and then maybe think about the analytical version. But there you go. Hope you had as much fun as I did troubleshooting. Wasted 6 minutes of video time. But there you go. I'll talk to you guys later.